Hello, my name is Robin Dupont. I'm a PhD student at Sorbonne University and I also work at Netatmo. Today, I'm going to present our work about extracting lightweight and efficient subnetwork from a large untrained network using Gumbel-Softmax. First, we will see why one would like to build lightweight neural networks. Then I will discuss about how to design lightweight neural networks with pruning. After that, I will present our method, I will share our results, and finally we will sum up what we saw. Why lightweight neural networks? Neural networks are usually trained and run on large and powerful servers. Many embedded devices would benefit from such algorithms, for example, autonomous vehicles, mobile phones, smart cameras, or even satellites. However, those devices lack computational power of the aforementioned server, thus there is a real need for lightweight neural networks. Lightweight neural networks can be obtained by pruning another network. Pruning consists in removing less important or redundant weights while trying to preserve the performances of the model. In our case, we use unstructured pruning, it is to say we remove weights independently. As a consequence, we obtain a sparse and lightweight neural network. Most pruning pipelines rely on a three-step procedure. First train, then prune, then fine-tune. First, the network is trained, then the least important weights are removed according to a criterion that is specific to each method. Pruning often reduces the performances, such as accuracy, of the network. That's why the network weights are fine-tuned. It allows to recover for most, if not all, the lost performance. Now let's talk about our method. In contrary to standard pruning pipelines, our method does not train the network weights. We only select the most useful weight without changing their values. Our pipeline is composed of two steps, training the parameters used for topology selection and pruning. Our method is stochastic. It trains the probability for a weight to be selected, here noted P cell, in the sample topology, which is then evaluated on the target task. Pruning the neural network, or selecting a topology, is in practice achieved by multiplying the weight tensor by a binary mask tensor. If a coefficient is 0, the associated weight is pruned. If it's 1, the weight is kept. Each coefficient m of the binary mask tensor is following a Bernoulli distribution of probability P cell. The objective is to train P cell using standard gradient descent. However, sampling is a not differentiable operation. To solve this issue, we use straight-through Gumbel-Softmax and reparameterize P cell as the sigmoid of m hat. M hat is the learned variable, whereas sigmoid ensures that P cell lies between 0 and 1 and therefore can be interpreted as probability. Gumbel-Softmax takes as argument the log probabilities of both outcomes. The first one is W being selected and the other one is W being pruned. So P cell and 1 minus P cell. Because of the combination of log and exponential function, this formulation is first computationally intensive and then subject to numerical instabilities. Meanwhile, our parameterization, called arbitrarily shifted log parameterization, ASLP, is much simpler. As a consequence, it is first numerically stable and then less computationally intensive than the naive formulation. Moreover, if our parameterization is interpreted as a log probability plus an arbitrary constant C, it indeed yields the same reparameterization as the naive formulation. C is an arbitrary constant, unknown, that shifts the log probabilities. Bear in mind that adding a constant to the log probability does not change the result of straight-through Gumbel-Softmax. Our method is composed of a second brick called Smart Rescale. Smart Rescale is a weight scaling technique. Each layer has its own scaling factor. Scaling the weight distribution allows to mitigate the change of variance due to pruning, since pruning removes weights from the weights distribution. Smart Rescale improves the performances as well as reducing the number of epochs needed for convergence. Here are some results of our method against the supermask method. The results are given for conv2 and conv4 network on CIFAR10 dataset. Our method consistently overperformed the supermask method in various contexts, it is to say with weight rescale, with sign constant, or with both. On CIFAR100, our method overperformed edge pop-up on most cases. Let's sum up what we just saw. First, we saw that lightweight neural networks are useful, especially for embedded devices. Then we saw that our method prunes untrained networks by performing topology selection only. We then saw that our method used Gumbel-Softmax in order to solve the problem of the sampling being not differentiable. Then we saw that ASLP is a simpler, less computationally intensive and numerically stable formulation. We saw as well that smart rescale improves the performances and reduces the number of epochs. Finally, our method yields lightweight neural networks without the need for weight training. Bear in mind that weights are not changed during the course of our procedure. That's it. Thank you for listening.